Hello, and welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 5, Section 2, Part 3. And today, we're going to be talking about the quantum atom. Okay, question for you is, why is the periodic table shaped this way and not like this? Because it would be a lot more efficient just to make it a box. Well, the shape of the periodic table is because of electrons. Electrons exist in energy levels or electron shells around the nucleus. The rows of the periodic table correspond to energy levels of the electrons. So let's pause with that thought for a second. So when we get out our periodic table, we see that there are two elements in the first row. And that first row is the same as the first energy level of electrons, which it can fit 2 electrons. And then we see on our periodic table, there are 8 elements in the second row, and then there are 8 electrons that can fit in that second shell. And then the third row, there are 8 elements in that third row on the periodic table. And we know that there are 8 electrons that fit in the third shell. So we know the first energy level can hold 2 electrons and the first row has 2 elements. The second and third energy levels can hold 8 electrons and the second and third rows on the periodic table have 8 elements. So let's take a picture of that. We've got our first row, 2 electrons, 2 elements. Second row, 8 electrons, 8 elements. Third row, 8 electrons, 8 elements. And then 4, 5, 6, 7, it gets a little more complicated. So we'll get into that as well. Okay, electrons in the outermost energy level are called valence electrons, and those are the ones that are involved in bonding. So that's where all the sexy things happen. That's where all the chemistry happens. The elements in the same column on the periodic table have the same number of valence electrons, and they have the same properties, and they bond in the same way. So please copy this down. In the first, just make a little periodic table, the first column has 1 valence electron, the second column has 2 valence electrons, third has 3, fourth has 5, fourth has 4, I should say the 13th column has 3, 14th column has 4, 15th column has 5, 16th column has 6, 17th column has 7, 18th column has 8. Okay, let's look at some examples. So we know elements in the same column have similar chemical properties. Let's look at group 1, the alkali metals. We see that they have 1 outer electron, 1 valence electron, and so they tend to donate that 1 electron. And if you donate 1 electron, you have a positive 1 charge, so they tend to form positive 1 ions. Lithium, sodium, potassium are 3 elements in there. So please write this down. Group 1, alkali metals, lithium, sodium, potassium. They have 1 more electron than a full energy level. So they have maybe their second row is full, and then in the third shell, they have 1 in there. So they really want to get rid of that 1, and then they have 1 extra proton, then electron, so they form +1 ions. They are very, very reactive. They really want to get rid of that 1 electron. Okay, let's go to another group, group 17, the halogens. So they're going to have 7 valence electrons, and all of these have similar properties, and they want to accept 1 electron because they have 7 valence electrons. They really want 1 more, so they take that electron. They've gotten 1 more electron, so they have a -1 charge. Fluorine, chlorine, and I should say fluoride ions, chloride ions, and bromide ions. So please write this down. Group 17, the halogens, chlorine, fluorine, bromine, iodine. They need one more electron to have a full energy level. So they form -1 ions, and they are very reactive. Okay, last example we're going to go over, the noble gases. So they have similar properties. They do not donate or accept electrons. They really tend not to form any compounds. They are satiated. They don't want anything to do with anybody else. So group 18, noble gases, neon, argon, they have full energy levels and are not reactive. Let's talk about the Bohr model. So atoms are too small to see, so how could we model them? The Bohr model is a good example. It shows protons and neutrons in the nucleus, and it shows the electrons as dots in shells or circles around the nucleus. First can hold 2, second shell can hold 8, third shell can hold 8, and so on. It's simplified, but it's still very useful. So it's more simplified than reality really is, but it's still useful. All right, please draw an example of neon, which would have 10 protons and neutrons in the nucleus, and then 2 electrons in the first shell and 8 electrons in the second shell. Okay, so I said it was simplified reality. The electrons aren't actually going around in an orbit like the planets around a sun. So if they're not orbiting, like where are they? What are they doing? Well, that is an excellent question. So that's kind of talking about the Bohr model versus the electron cloud model. So as opposed to being in organized orbits, they are in areas of probability. So in reality, electrons exist in orbitals. So please write this down. Electrons exist in pairs in orbitals. An orbital is an area of the electron cloud that has a specific shape, that has a spatial shape. Shape in space, a 3D shape. So we call them S, P, D, and F. The S orbital is the lowest energy. It can hold 1 electron pair, so it can hold 2 electrons. P's can hold 3 electron pairs for a total of 6 electrons. D's 5 electron pairs for a total of 10 electrons. And F's 7 electron pairs for a total of 14 electrons. And these orbitals correspond to actual areas on the periodic table. Okay, so please make a simplified drawing of this in your notebook where the left 2 columns plus helium are S block elements, and then over here these are all P block elements, and D block, the transition metals, and then down below is our F block. So if we notice, we said the the S orbital can hold 2 electrons. Look at this, 1, 2, coincidence? We said P orbitals can hold 6 electrons. So you want to count that out, 6 elements. D block, 10 electrons, 10 elements in a period. And then guess how many elements can fit in the F block. Okay, so the orbitals are actual shapes around the nucleus. So S is a sphere. P's kind of look like dumbbells. So there's like one on the X axis, one on the Y axis, and one on the Z axis coming towards you. And then once you get into the D and the F, they just get like crazy shapes. So the first energy level is a lower energy, and then each energy level, second, third, fourth, and fifth, are higher energy levels. Okay, why do different elements have different properties? Well, we know electrons are responsible for these chemical properties, but why do electrons behave the way they do? Mr. Niels Bohr has the answer, as part of the answer, with quantum theory. Quantum theory explains how the universe behaves on a very small scale. So let's dive a little bit into quantum theory, just a little bit. The theory of chemistry and physics that describes the universe on a very small scale, like inside the atom, which is teeny tiny. Please write these things down. The theory gives electrons a quantum state, a specific combination of energy and position. So it's like their state can be quantified, like with numbers that tell us about their energy and their position. At the size of an atom, I'm just going to let you know the way you're thinking about it's wrong. Atoms, electrons do not work the way our brains work. So at the quantum level, a particle is not like a tiny ball that is distinct and it has boundaries, but its mass, size, and location are all like spread out in a wave. So you don't have to write these down, but please pay attention. On the scale of atoms, a particle of matter such as an electron is not a solid, but it is smeared out in a wave over a region of space. And when electrons are confined in an atom, their wave properties force them into a pattern, and whatever pattern they choose is the one that's going to minimize the amount of energy. And each unique place in the pattern is a quantum state, and it can only hold one electron. So one electron per quantum state. And electrons are always found in a quantum state or another one, never in between, in one or in another one. And no two electrons can be in the same quantum state at the same time. Okay, so let's look at a wave and a particle. So a lot of times we think about light as moving in waves, where it's a transfer of energy but not matter, and we think of electrons like as particles, like protons, neutrons, and electrons. Protons and neutrons do act a lot like particles, just not electrons. So we often think about light as a wave, electrons as particles, but they're both way more complicated than that. Light is a wave, but also it travels in packets of light, like bundles of light and photons. You can only have like a whole number multiple of a certain number of photons. You can't have half a photon. And electrons often behave like waves. So it's more like this. And we know from waves from freshman year that waves have a frequency, which is the rate at which a point oscillates. And they have a wavelength, which is the actual length between like a crest and the succeeding crest. And we know if the frequency increases, the amount of energy it transfers increases. And we know higher frequency, like I said, is higher energy. So let's just take a look at these crazy looking complicated equations. So one is Planck's constant, H, if you can see, is both found. It's this fundamental constant. It's found in the light, over here, the light equation, figuring out the energy, if you know the frequency of light. And then it's also found in dealing with the electrons, figuring out their wavelength, mass, energy. Okay, wave addition. Waves can do math. So if you have one wave and another wave, and if they line up, you get a bigger wave. Kind of like if you have one ball and another ball, you have two balls. However, waves subtract. So if you have the crest of one wave lines up with the trough of another wave, they just cancel each other out. So two waves could equal 0. Okay, so imagine a wave in a box, and that's wave 1. And then that wave bounces off the wall and comes back, and we're going to call it wave 2. If those two waves are set up so that the crest and the trough cancel each other out, we have no waves. Well, what does that have to do with electrons? I'm going to leave you with that cliffhanger. What do waves and waves adding and waves canceling each other have to do with the electrons? I will see you in part 4. Bye.